Let's now talk about a new sorting algorithm. So far we have covered the merge sort, which is n log n, and also previously we covered the two quadratic sorting algorithm, which are the selection sort and insertion sort. This will be our fourth sorting algorithm. And there's another fifth one which will be covered when we talk about a heap data structure, which is for the heap sort. Just remember, in this course we actually cover 5 sorting algorithms for you to actually learn. Alright, for the quick sort, as usual, let's now go over the intuitive ideas about how the sorting algorithm works, and then we'll go over the Java code for implementation, and then we'll analyze the running time. That'll be the usual workflow we should really go through to learn about a new algorithm. And the sorting problem is something that we have seen many times. No precondition. The input list or input array of numbers can be arbitrarily arranged. And then you want to produce another sequence, the output, that's going to be sorted in a non-descending order. And we talk about other possibility as well for ascending, non-ascending, and etc. That's something you want to review from the previous part of the lecture as well. And what will be the recursive algorithm for the quick sort? What will be the idea? And let's talk about base cases first before we talk about a recursive case. What if the empty list as the input is given? In that case, it's automatically sorted. That'll be bigger of 1. And what about the list contains only 1 element inside? In that case, it will also be automatically sorted. So these are the 2 same base cases for any sorting algorithm. And let's now talk about the recursive case. Let me sketch the idea together with you, and then we'll go on to the Java code. And there's one thing I would like to show to you first of all. For the recursive case, we want to basically choose something called a pivot. I want you to see this word right away. This pivot basically is going to decide how we are going to split the list into 2 halves. And the pivot has to be chosen in a very careful way. Let me just do a comparison right away. In the case of the merge sort, when we actually choose the to actually split the list into left and right, we simply choose the middle point. However, for the quick sort, as we will analyze the running time later, choosing the middle or choosing somewhere without any consideration may not be a good idea. You can easily run into some very inefficient algorithm for the sorting. That's something you want to keep in mind first. Alright, so having this word seen, let's now talk about a general idea about a quick sort. Let's say you're given some input list which is just not sorted over here. And the idea would be we want to choose something called a pivot. And the pivot can be chosen anywhere in the list. I'll talk about what might be the best strategy for you to actually choose. Ideally, you want to choose a pivot. Okay, so pivot, P-I-V-O-T, V-O-T. And ideally, the median value of the list elements. And you will see what it really entails when it happens to be the median. I'll talk about how we can use the pivot first. So the pivot, we said ideally, as far as the runtime is concerned, it better be the median value. That's something I want to give you some advice right away. And that's something you want to keep in mind as well when you actually implement your quicksort algorithm in some programming language. Once we choose the pivot, for example, let's say we simply choose the last elements as a pivot. Let's say this one over here is the pivot. Once we have chosen a pivot, let's say this is the pivot. Okay, let me just try to make it more obvious to you. Let's say this is the pivot we have chosen. And conceptually, think about the pivot is actually going to occur conceptually in the middle. And we're going to go through the rest of the list over here. For any elements that is less than or equal to the pivot, we're going to put it on the left. For any element that's strictly larger than the pivot, we're going to put it on the right over here. That's what we're going to do. We are not really sorting them, but in some way we're just doing comparison, right? So what I will do is I'm going to say for this part over here, right? Let me just make it a little bit smaller. Okay. You can think about we're going to produce the left half and also the right half. Okay, let me use maybe purple. The right half. over here. The idea would be, number one, given the pivot is actually in the middle, this part over here will be all elements strictly less than the pivot. And this part over here will be all the elements strictly larger than the pivot. And of course, this part over here can be a little bit more relaxed. Less than or equal to will be okay. Sometimes you might contain duplicates in your list, so that'll be okay. Right? Just remember less than or equal to and also larger than. Once we got this intermediate list, we're going to recur on the sorting algorithm. So remember in the beginning, we're actually going to call the sort over here on the entire list. And the step we just did was to choose the pivot and also split. And the split in the QuickSort is going to be more expensive than the splitting process in the merge sort. In the case of the merge sort, you simply choose the middle one and then split the list into two halves. However, in the case of the QuickSort, so let me just put it down. So this step over here is the first one, which is to choose the pivot and split. So split with respect to the pivot chosen. So you cannot just arbitrarily just put any element that you found just to the left or to the right. It has to be based on the relation inequality over here. Right, so this one turns out is going to take linear time to really complete, but we'll talk about it more precisely a little bit later. And after we have done the split according to the pivot, we're actually going to recur on the left and also the right. Meaning that, let me just make it a little bit smaller. I think I definitely need a little bit more space over here. Let me just make it smaller. Okay, awesome. That's good. And what we have is, we have this part over here, that's the left. And we have this part over here, that's the right, right? Left and right. And we're going to call the sort method recursively, the sort over here, and also the sort over here. Each one of them is going to return the sorted list. Right, so here's my question for you. If you recall what we said about the merge sort, once you have recursively sorted the left half and the right half, in the case of the merge sort, you still have to merge them. And the merge routine is actually a more expensive routine, which will take linear time. But in this case, given that we have recursively sorted this list and also recursively sorted this list, if we want to combine these two lists together with the pivot that we have chosen, how much time should it really cost? It turns out it's only constant, because remember before we actually made the recursive call, every element on the green portion is guaranteed to be less than or equal to the pivot. Every element in the purple region is guaranteed to be strictly larger than the pivot. So after you have sorted them, there will still be every element is larger than this pivot. It's just that they have been sorted. Similarly, every element in this sorted portion over here is still less than or equal to the pivot. In order to really make an overall answer as a sorted list compared with the original version, all we gotta do is you simply concatenate this list with this element and with this list. That's all we gotta do. Alright, so what we're gonna do is, let me just say the final one, we're just going to concatenate. And the way we're going to do that would be, let me just say this. So we still have this middle elements over here. And then the sorted one is going to be, let me just say this one is the left sorted version. And this one over here would be the right sorted version. We can just concatenate them together, and this will be the final answer compare with the original list. That's the QuickSort. Let me recap very quickly. Given this original unsorted list, if we want to sort it, first of all, we're going to choose a pivot. Let's say we choose the last element as a pivot. And then we're going to put a pivot in the middle and put everything that's less than or equal to the pivot to the left. Everything that's larger than the pivot to the right. And this part over here, as we'll see, will take linear time. And then we're going to recursively sort everything that's less than the pivot together. And we'll get some lists like this. And we're going to recursively sort everything that's larger than the pivot. In that case, we're going to get this particular sorted list. After that, given that every element over here is less than or equal to this, you can think about it's more like a left subtree in a binary search tree with respect to the root. And this part over here is a bit like a right subtree of the root in the binary search tree context, right? And finally, this part over here is really the sorted version. This part over here is really the answer. Okay. Oh. Right. Let me just put it down, and we are done with the intuition. So this will be the sorted version of the input list. And you may just want to compare and contrast right away between the QuickSort and also the merge sort. In the case of the merge sort, what really cost for the running time is about the merge routine, which will take n. But in the case of QuickSort, we don't really need any merge. We only do concatenation. What really cost for the runtime for every level of recursion is going to be how we actually split the original list into two halves based on the pivot. That's really the more expensive bit. Just remember that insight. Alrighty, let's now take a look at how we can implement a QuickSort in Java.